You know, they say that once the mind is expanded, it cannot be contracted again. I've got one thing to say to that. Let the expanding begin right now. You're about to be expanded. My friends, prepare for glory. Tonight we dine in elegance. Here we go. Today's a fundamental theorem of calculus. Today we put the age-old question of adding infinite many little things with that are infinitely small. And today we don't add them the Riemann sum way like we did before. Today we take it 1,000 notches above that, okay, to a totally different new level. And we will make child's play out of this problem, out of this age-old problem. Problem that started with at least 2,000 or 3,000 years ago. So to begin with, let me tell you, we need some ingredients, or should I say, we need one ingredient. Haha, just one is all we need, and that ingredient, of course, is the mean value theorem. It plays such a prominent role in this idea, and in fact, in all of calculus. Really, it should be called the MVP. MVT is the MVP of calculus. Let me just remind you in 2 seconds what it said. It said if you've got some function here, some nice little function here, with suitable conditions, meaning continuous, bounded, well-behaved, blah blah blah, and suppose we're considering finding the area from some point A to some point B. So let's mark this say point A and this point say B. The mean value theorem said if you take a look at the secant slope, that would be f of b minus f of a all over b minus a. There's always some point in the middle guaranteed by the mean value theorem under the right conditions, such that the tangent slope at that point is achieved to be exactly the same as the secant slope, meaning that this secant slope would be equal to the tangent slope for some point C in the middle. That's what the mean value theorem says. But that's not really the most powerful form of it. We just tweak it just a little bit and make it unleash the power. The way we tweak it was we multiply both sides by b minus a, and that would give us a new statement. It would tell us that f of b minus f of a is equal to f prime of c times b minus a. That would be a slightly improved version of the mean value theorem. It's the same thing, it's just rewritten a little bit different, and this is the way it becomes much more powerful. In fact, we'll take it even one step further. This is a review from a previous lecture, by the way. We've done this before, but let me just remind you. The reason it becomes powerful is because you can set up this exchange rate between the left side and the right side. Again, this is just a rewrite of the mean value theorem, but you could say, well, what if I had some function, capital F of x, whose derivative is f of x? Think about that for a second. That means that f of x is the antiderivative, capital F of x is the antiderivative of f of x. That's what this statement is saying. I'll give you a quick example just so we're all on the same page. Suppose f of x is equal to 3x squared. What would that make f of x, the capital F of x? Well, that would make it a function such that if I take the derivative of this, I get 3x squared. Now thinking that would make it a function such that if suppose I tell you, hey, I've got a function in my hand right here, and I won't tell you what it is, but I'll tell you something. If I take the derivative of this function, I get 3x squared. Can you guess what the function is? Can you guess what the function is? And if you guess x to the third, you've guessed it correctly. Because look, if I take the derivative of it, I get 3x squared. That's the relationship between the capital F and the little f. I'll do it again. Suppose I tell you f of x is equal to cosine x. What would that make capital F? That would make it a function here inside my hand. I won't tell you what it is, but I'll give you a hint. If I take the derivative of it, I get cosine x. What would that function be? Well, possibly it could be sine x, because if I take the derivative of sine x, I do get cosine x. And so that's the relationship between capital F and little f, meaning that if you take the derivative of capital Fx, you get little f. Now we're trying to make the exchange clear for this is just a new version of, not new, it's just a slightly tweaked version of the mean value theorem. So here's the most important version of it. If I have f of c times b minus a, I could exchange that for its antiderivative f of b minus its antiderivative f at a. This is the unleashing the power of the mean value theorem. And I know you're not supposed to see why yet, but I'm just trying to prepare you. This is an incredibly useful statement that we'll come back to over and over again throughout the lecture. Capiche? Alright, that's it. That's the ingredient. There's only one ingredient, the mean value theorem, dressed up this way. How many ingredients are there in this lecture? One. One ingredient. The most valuable player, the mean value theorem. That's it. And it's dressed up in this way. Okay? I think we've made that clear. This is it. This is the most important form of the mean value theorem. Wow, that's it. That's all we need. Prepare for glory. Now we're ready to put to bed this age-old problem. The Riemann is okay. The Riemann, the limits save the day for the Riemann sums. The limit is still king, but the king is about to be dethroned with sheer beauty, elegance, and creativity. All right, enough talk. Let's do it. Okay, my friends, prepare for glory. You're about to dine in elegance. Let's do it. I'm tired of talking about it. Let's do it. So let's put this guy off to the side for a second. This is what we want to find, the Riemann sum from 2 to 8. But let's put it aside for a second. Let's just be happy with, say, finding something like, I don't know, let's just say be happy with finding something like A3, meaning the area when we cut it up into 3 little rectangles. Once we find A3, we can find A4, A5, etc., and we'll find the actual Riemann sum limit. So for 3, we would slice it up into 3 pieces, and we'll go with uniformity here, all uniform size. And we'll make the usual little rectangles. There you go. And then we're going to be very, very cautious about the height that we choose for each one. We know this is A1, the first little area, and we know this is A2, the second little area, and this is A3, the third little area. And before, we had contemplated finding the height of A1 by plugging in 2 into the function. So if you did that, this would give you the height, and this would be your area. We had also contemplated using the right sides, which would give you this as an area. But the truth is that because ultimately we're going to take very, very large number of rectangles, the difference will be negligible. And so we could take any point in that middle for that matter, so long as the function is defined there and bounded, which we're assuming this is a nice function. Any point in the middle will do. What we're going to do is choose an incredibly important point in the middle, we'll call it C1, guaranteed by the mean value theorem. At this point, something very, very special happens. The tangent slope is equal to the secant slope, right? Somewhere in here, there's a point, maybe it's more to the right, where the tangent slope is equal to the secant point. That's what I'm going to use for a height. And so my first little area will be calculated using exactly that height. What I'm saying is that A1 would be equal to, in that case, A1 would be equal to the height times the base. And for my A1, the height would be f of C1. And the base, well, the base I could go like this. I could say, hey, well, how wide is it from 4 to 2? I could say, well, that distance is 4 minus 2. And I'd be happy with that. You don't want to simplify. Every time you simplify, you hide the patterns of the universe. Do not simplify. Leave it like that. And be happy with it. And let's go with A2. A2, we're going to play a similar game. We'll imagine that there's a secant slope here, and somewhere within that interval, there's a place here, C2, such that at that point, C2, the tangent slope is equal to the secant slope. That's what we're going to use for a height on the function. We'll use, for A2, would be f of C2 times 6 minus 4. The height times the base. The height would, again, is being calculated very judiciously at this point, guaranteed by the mean value theorem. They only had one ingredient for this lecture, one ingredient only, the mean value theorem. That's what's helping us choose which point within the interval that we're going to use to calculate the height. We use that point to plug it into the function and get the height. Same thing for A3. A3 would be equal to f, the calculated height at some very, very special point, C3, times the width of the interval, which would be 8 minus 6. Giving us some height more or less like this, and there you go. So A1 would be the first little area plus the second little area plus the third little area. That would be my area of 3 rectangles. Now let's look at that more carefully. A3 would be equal to A1 plus A2 plus A3, and we say that's equal to f of C1 times 4 minus 2 plus f of c2 times 6 minus 4 plus f of c3 times 8 minus 6, right? Now, what exactly happens here is the most important part of the lecture. We only had one ingredient, right? What was the one ingredient? The mean value theorem. The mean value theorem says every one of these creatures that look like this, f of c minus f of c times b minus a, for a carefully chosen c, which we did, can be exchanged. You can throw that away and change it for the antiderivative evaluated at b minus the antiderivative evaluated at a. Let me say that one more time. That one more time. I'm just kidding. Let me say this one more time. Every time you've got the c chosen carefully, this quantity f of c times b minus a, which in our cases, these are little areas or little rectangles, can be exchanged for the antiderivative at f minus the antiderivative of a. Antiderivative of f at b minus the antiderivative at a. Let's do it. So what does that mean for our case? This one right here. This one can be exchanged. This one can be exchanged. I can exchange it for a capital F, which would be the antiderivative of that, at 4 minus a capital F of 2, plus a this one I could exchange it, capital F at 6 minus capital F at 4, plus this one I can exchange, capital F at 8 minus capital F of 6. You say, whoa, 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 whoa. What happens now? I told you, this is where the glory comes in. Something amazing is going to happen right now. Look, I'm going to look at this sum and say, whoa, 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 a bunch of things are canceling. That f of 4 cancels with that one because that one's negative and that one's positive. That f of 6 cancels with that one because that one's positive and that was negative. In fact, if I had a whole bunch of them, exactly the same thing would have happened. And so I would get that A3 is only the next to the last, which would be F8 minus F2. And say, whoa, 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 whoa. That can't be. Maybe that we just got lucky. That was for A3. What if it was a different A? What if we had cut it up into, I don't know, 5 or 6 little rectangles? Would the same thing happen? Or maybe things would go work out differently. Well, let's take a look. Suppose you cut it up into 6 pieces, 6 rectangles. So then our rectangles would go from, they would take all the intermediate values here from 2 to 3 to 4 to 5 to 6 to 7. You'd have all these intermediate values here plain, and you'd have a lot more of these. So the A6 would really look more something like this. F of C1 times the width, 3 minus 2. F of C2, 4 minus 3, etc., etc., etc. I've got all my little areas, A1, A2, little area 1, little area 2, etc. And then, of course, we would invoke the power of the most valuable player in here, the mean value theorem, that says every one of these can be exchanged for that. So I would do exactly that. Every one of these I would exchange for the mean value theorem version of the antiderivative evaluated at the endpoints. Boom, and that's what I would get. And then what would happen? We have a huge miss. Not to worry. Tonight, we don't worry. Here's what happens here. Look at this carefully. F of 3, this capital F of 3 would cancel with that one because one is opposite, one is negative. Yippee-ki-yay. Wait, there's more. This F of 4 would cancel with that one. This F of 5 would cancel with that one. This F of 6 would cancel with that one. This one would cancel with that one. I told you. Didn't I tell you? What would be left over at the very, very end? Only the next to the first and next to the first, next to the last and next to the first terms. Giving you this amazing statement. A6, the area for 6 little rectangle subdivisions, would be equal to the antiderivative at 8 minus the antiderivative at 2. But wait a minute, isn't that exactly the same thing we got for A3? We got the antiderivative of 8 minus the antiderivative of 2. Yes. And we did it for 6 and we got the same thing. What do you think would happen if we did it for A7? Well, I got a prediction for you. We would get f of antiderivative at 8 minus the antiderivative at 2. What if you did it for A3512? Well, I've got a prediction for you. It would be the antiderivative at 8 minus the antiderivative at 2. Whoa, 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 whoa. What's happening here? This is telling you that, you know what this is telling you? This is telling you something amazing. Let's clear this page and make room for the amazing. This is telling you that if I took the integral from 2 to 8 of my function f of x dx, which is defined to be the limit, roughly speaking, this is not exact, but roughly speaking, the limit as p goes to infinity of the sum of all my little p rectangles, and I've calculated the sum here. I've got this amazing calculation that says that, hey, I'm going to go with yellow here. The sum of p little rectangles, no matter what p is the antiderivative at 8 minus the antiderivative at 2. Yeah? what would happen if I slap a limit on both sides? Limit as p goes to infinity, and the limit as p goes to infinity. Well, this is independent of p. It wouldn't have mattered if you'd cut it up into 2, 1,000, or 5 billion pieces. It would still be telescoping. Everything in the middle would cancel, and we would get that this limit, this is a limit of a constant, so it's still the same. This is a constant, that's a constant. The limit does nothing to it. But on the other hand, this limit turns into the integral. And we get the amazing statement, the fundamental theorem of calculus, the jewel of the 17th century, one of the 9 symphonies for humans. Bam, right there. It's telling you that to calculate the area, all you need is find the antiderivative, evaluate it at 8, find the antiderivative, evaluate it at 2, and yippee-ki-yay, you're done. Wow, that's amazing. Let's take a look at an example. The integral from, say, from 0 to 10 of this function, and suppose this function is 2x dx. Okay. Of course, you could do it the old way, and we'll do that later. But let's just flex the fundamental theorem of calculus muscles for just a little bit. The fundamental theorem of calculus would say, hey, that's your f of x right there, your 2x. Suppose you could find an antiderivative of that. All you would have to do is find that antiderivative, evaluate it at 10, and find the antiderivative, evaluate it at 0, and you'd be done. So then you start to think, oh my goodness, now we have to be good at antiderivatives. How do we find antiderivatives? And so you go off to the side and say, hey, I've got a function here in my pocket. I don't know what it is, but all I know is that its derivative is equal to 2x. So you think, which function is there that when you take the derivative of it, you get 2x? Well, if you've done enough derivatives, if enough homework, you can actually take a stab at this. It's a reasonably easy question to answer. The answer would be x squared. That would be your function. Your function is f of x squared, such that when you take the derivative of it, you get 2x. And so, all you'd have to do here is do 10 squared. So that would be 10 times 10 minus 0. Well, you plug in 0, then you're done. And so that minus 0 times 0, then you're done. So that's 100. That's it. Which is a super fancy way of saying that the area of a triangle here, this is 10. If this is 10, the height would be, f of x was equal to 2x. So if x is 10, the height would be 20, and the area would be 10 times 20 all over 2. So that would be 10 times 10. This is a super fancy way of saying that the area of this triangle is 100. But wait, there's more. Of course, this is so much more powerful than triangles. My goodness. Anything you can think about. Take a look at this function. We've tried something like this before using the Riemann sum and the limit. The limit was the king. And I say was. The king has been dethroned with this amazingly brilliant idea, the idea of the fundamental theorem of calculus, which says, hey, suppose you wanted to find the Riemann sum from 0 all the way to, 4. For this function, 3x squared dx. These are all the little areas, the height and all the little widths. The fundamental theorem of calculus would say elegantly, I may add, it would say, hey, don't even worry about it, chump. All you gotta do is find out the antiderivative, evaluate it at 4, find out the antiderivative, evaluate it at 0, and subtract them, and yippee-ki-yay, you're there. So then you start to think, oh my goodness, I've got a number, I got a function in my pocket, I don't know anything about it, but I know that if you take the derivative of it, you get 3x squared. And you start to think, well, if I took the derivative, I would bring the power down and subtract 1, so the power's got to be 1 more than that one. And then you divide by it, so if you think about it for about 5 or 10 seconds, you realize that function has got to be x to the third, or at least that's a feasible choice. If you take the derivative, let's check it. If you take the derivative of x to the third, you bring it down, that would be 3x squared. This is perfect, it checks, and now it's all over, because look at this. All I'm going to do is take my 4, plug it in there, 4 to the third, minus, I take my 0, plug it in there, 0 to the third, yippee-ki-yay. That's how we roll, that's how we do it nowadays, huh? That's how we find areas under the curve. An amazingly elegant idea, the fundamental theorem of calculus. Okay, want to see it again? I'll show you again. Have you ever wondered, what is the area underneath the cosine graph? For example, from here to here, how much area is there? Keep in mind, you should be able to give at least a common sense approach to this problem. Look, I'll give you 1 unit. This is approximately 1 square. So the question is, how many of these 1 squares fit in there? Or how many of these 1 squares fit in there? You know, questions like that. Well, the Riemann integral would say, hey, you find this limit, which goes more or less like this. You find that area would be equal to, you find this limit which goes from 0 to pi over 2 of cosine x dx. That would be the function, f of x. Every one of these little rascals, differential of x is the width, and the height would be the value determined by the cosine function. And you're adding them all up from 0, sum from 0 all the way to pi over 2. And then, if this was yesterday or before watching this video, you would have sat there and find limits and blah blah blah. No, 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 no. Tonight we dine in elegance, my friends. Tonight we've got the fundamental theorem of calculus. Your mind has been expanded. Once your mind is expanded, it cannot be contracted. It says all you got to do is find the antiderivative, evaluate it at pi over 2, find the antiderivative, evaluate it at 0, and yippee-ki-yay. So then you start to think, all right, I've got a function in my pocket. I won't tell you what it is, but I'll give you a hint about it. I've got a function in my hand. Oops, it's in the other hand. Nope, it's in this one. All I'm going to do is give you a hint about the function. If I take a derivative of the function, I get cosine x. The question is, can you guess what the function may be? The truth is there may be more than one, but can you at least tell me one? Well, if you think about it enough and you've done enough derivatives, you realize that it's sine of x. Sine of x would be a feasible choice. Let's check. If you take the derivative of sine of x, what's the derivative of sine of x? Cosine x? Told you. Didn't I tell you? That's why they pay me. So, I've got my number, I got my function in my antiderivative, it's sine x. All I got to do now is evaluate it here. Sine of pi over 2 minus sine of 0. And that was sine of pi over 2. Well, that would be 1 minus sine of 0, that would be 0. So that's equal to 1. Yippee-ki-yay. That's why they pay me. This is saying that the number of this 1 unit squares that fit into this little area is exactly 1. Of course, you could probably guess what it is in here now. By the symmetry of the cosine graph, this little hill would have 2 of these pieces, because that's just half a hill. So you could guess that the area here would be 2. But more than that, if I took the integral from here to here, I bet you I'd get negative 2 because the area is below the x-axis, and all these f values are negative. If you don't believe me, we could try it. Want to try it? Or are you afraid? Or you got something better to do than to dine in elegance? That's how we do it. Let's do it. Talk is cheap. So now I'm contemplating a slightly different question. By the way, this is, I think, pi over 2. This would be 3 pi over 2. And this would be the cosine x function dx. And I'll make a picture. This is exactly what I'm considering here. The Riemann sum for this region. Okay? But forget Riemann sums. That's so 2000. That's so 1800. No. That's so 520 BC. Forget that. We got the fundamental theorem of calculus, powerful, elegant, which says, hey, don't even worry about it. Just find the antiderivative, evaluate it at 3 pi over 2. Find the antiderivative, evaluate it at pi over 2, subtract them, and you're good to go. So you think, all right, we already did this. We already played the game. The antiderivative is sine. So sine of 3 pi over 2 minus sine of pi over 2. And this would be equal to negative 1 minus positive 1, negative 2. I told you. Didn't I tell you? Didn't I tell you? You see why they pay me? Insane amounts of money. Alright. How about some more classic examples? I'll leave that one alone. Classic examples. Y is equal to 1 over x. Okay? Super famous. Have you ever wondered on 1 over x, if I wanted to find the area, say, I don't know, say from 1 to 4. What is that area? You guys ever wonder? I've wondered. From 1 to 4, what is this area? This little guy right here. Little tiny area. Well, how much is it? It's so easy now. The fundamental theorem of calculus has made child's play out of this. We would say it's the integral of 1 over x dx as x runs from 1 to 4. And the Riemann sum would go on with these limits and stuff, but the fundamental theorem of calculus has better ideas in mind. Fundamental theorem of calculus says, hey, this would be equal to the antiderivative at 4 minus the antiderivative at 1. And then you start to think in your mind, hey, I've got a, maybe right here on the side, I've got a function in my pocket. I won't tell you what it is, not in my hand, but I know something about it. If I take the derivative, I get 1 over x. Then you start to maybe go through the catalog in your brain of all the functions that we know and try to think, are there any of those that we know whose derivative is 1 over x? Or you may want to look at the famous sheet that we posted on MathHands that had all the famous derivatives, and maybe scan through there if if it doesn't come to mind right away. But after a few seconds, it should come to mind that function is ln of x. If you take the derivative of ln x, you get 1 over x. So therefore, we're in business. It's all over now. Watch this. This would be ln of 4 minus ln of 1, which, incidentally, ln of 1 is 0, so the grand total is ln of 4. Did you ever think that you could calculate errors with such elegance and grace in your lifetime? When I was a little boy, I never thought I could ever calculate errors with such elegance and grace. It's such a nice idea to learn. I love it. I told you, in calculus, there's only about 1 or 2 amazing ideas that change the world forever, and the rest of it is pretty much grunt work or a little redressing of the same ideas. This is not a redressing of anything. This is it. This is one of the most beautiful ideas that you will learn in this class, and perhaps in many classes. Such creativity and such an elegant conclusion to such a difficult problem, right? Anyways, talk is cheap. Let's do it one more time. Some classical stuff. F of x is equal to e to the x. Super famous exponential function. Let's go from 2 to, I don't know, whatever, 5. And then let's ask the question. The question everybody wants to know is, what is the area? Huh? So then you think, well, I could write it in terms of integrals. This would be the integral of e to the x dx as x runs from 2 to 5. And the fundamental theorem of calculus, of course, has something big to say about that. It says, hey, don't even worry about it. Find the antiderivative valued at 5 minus find the antiderivative valued at 2, and you're done. By the way, sometimes I get tired of writing this, and so do other people. And so people have agreed to use the following notation. They'll just use f of x, and they'll use a little line here, say 5, 2. And that's just supposed to be a convenient way of writing f of 5 minus f of 2. It means you plug in the 5, and then you plug in the 2 and subtract them. That's super famous notation. So, or sometimes they make these little square ones. Same thing. In any case, I got to find the antiderivative. So then I get to play that little antiderivative game again. I say, hey, I've got a function here. All I know is that the derivative is e to the x. But I'm trying to guess, what function was that? Where did it come from? I need a function such that when I take the derivative, I get e to the x. So again, you could look through all your famous functions, famous derivatives. Are there any of them whose derivative is e to the x? And the answer is yes, of course. E to the x has its own derivative, e to the x. So it's all over now. That means that this one would be equal to e to the 5 minus e to the 2. And that, my friends, that's how we do it. Pretty nice, huh? Wow. If I was a theorem, maybe I would like to be this theorem. Nah, maybe. I don't know. It's one of my favorites. It's one of the 9th symphonies of humans. Humans have created 9 symphonies. This has got to be on the short list of the for anybody who's been around for a while. This has to be on the short list. Fundamental theorem of calculus, such an elegant solution. I think that will do it for us today. The only thing left to do is now we turn our attention. You see, this puts a huge price on antiderivatives. Antiderivatives become of the utmost importance now that we've seen the fundamental theorem of calculus. And so the next few chapters, the next few sections, we will turn our attention solely on antiderivatives. That will be the name of the game for the next few sections, and you'll see that actually some of them can be a little bit challenging, which is nice. Derivatives were so easy. That's where we'll be headed next. Okay.